Okay, so now let's see how we can use this bootstrap distribution to build some error into our original estimate. So let's say the problem here is we're trying to estimate the mean amount of arsenic in the groundwater in Bangladesh. We'll call that population parameter mu. We picked a sample of 271 water samples, and we found the mean to be 125 parts per billion. So that would be our first guess. We would call this a point estimate. So we're estimating this parameter with one single value. But we should be aware that our sample mean is not going to be a perfect estimate for mu because we don't have all of the data from the population. So what I'd like to say is the mean amount of arsenic is 125 parts per billion, plus or minus some error. So how do we figure out what is a reasonable amount of error to build into that? Well, we can use the bootstrap distribution, and in particular, the standard error of that bootstrap distribution is going to give us a good estimate for what the standard error of the actual sampling distribution would be. And this standard error, one way that we can think about it is it quantifies the variability in sample statistics due to the randomness of sampling. And what we found previously is that if I were to take the standard error of all of the bootstrap means, that came out to about 18. So what we recall from like the empirical rule, for example, we could say that 95% of all bootstrap samples are between the mean, which was 125 plus 2 times the standard error, and 125 minus 2 times the standard error. So this one winds up being 161. And for the lower estimate, we would get 89. And so if we think back to the empirical rule, so that means from about here at 89 over to here at 161. So we can see that most of our bootstrap samples had a mean between 89 and 161. So therefore, we could say that since most of our samples are going to be between these two values, it's a pretty good guess that the overall population mean is going to fall between those two values. We can calculate this more precisely using R. And so looking down here at the R code, what I've actually done is if I boot mean, this was where all of the means of each of the bootstrap samples was stored. And what this is doing is it's saying find the 0.025, 0.975 quantile. So in other words, we're looking at the 2.5 percentile over here and the 97.5 percentile over here. And in between those two are the middle 95% of the values. So this is not exactly what we got when we did the empirical rule, but it's pretty close. So what this is saying is the middle 95% of our bootstrap samples fell between 92.69 and 163.8. And that now gives me an interval estimate for the population mean. I would say that the population mean, the plausible values for the population mean fall somewhere between 92.7 and 163.8. Okay, so let's kind of generalize this concept of these interval estimates that we just looked at with the arsenic example. So what we just constructed is an example of what's called a 95% bootstrap confidence interval. So when we look at the 2.5 and the 9.75 percentiles of the bootstrap distribution, we use those as the cutoffs for our interval. Then what happens is that interval has a 95% chance of containing the actual value of the population parameter we're trying to estimate. And so this 95% this is the success rate that that interval might have. So sometimes if we start with a biased sample, then the resulting bootstrap distribution that we construct is going to be biased, and our interval, it might not actually contain the population parameter we're trying to estimate. But if we follow this procedure, the success rate is going to be about 95%, and we call that the confidence level of the estimate. So I want to just be really careful about the language that we use here. And that is when we're interpreting these interval estimates, we want to be really careful here that the uncertainty is attached to the interval and not the population parameter. Okay, because the interval that we constructed, well, that was based on some randomness, right? That was based on the random sample that we picked. So there is some uncertainty in that quantity and those cutoffs, but we shouldn't attach this uncertainty to the population parameter. There's nothing random about the value of the population parameter. It is what it is, just we don't know what it is. So when we're stating this, we want to be sure that you're careful. And so over here, this is a don't. What we don't want to say is there's a 95% chance the population parameter is in the interval. Okay, and the reason why we don't want to say that is because this uncertainty, when we say it this way, is being attached to the population parameter. And that is not random. So when we say this, we want to be sure that we attach this uncertainty to the interval, as we did in this first bullet over here. So just to be clear, I'm going to put an X through that. So if you didn't hear that, just pretend you didn't hear it, because I was explaining this is the wrong way that we should do things. So what we want to do is attach this uncertainty to the interval that we've constructed. So this is a point that we'll be sure to emphasize when we're interpreting these results.